This chart shows inference throughput measured in tokens per second, and right here is a massive anomaly. A single chip serving the Llama 3.1 8B model at a blistering 16,960 tokens every second. That specific speed claim is the driving force behind a definitive agreement announced in August 2026. AMD is acquiring Taalas, a Toronto-based startup founded in 2023. Taalas achieved this throughput on their first test chip, known as the HC1. It is built on TSMC's 6-nanometer process, packing 53 billion transistors into a server running at 2.5 kilowatts. In their February 2026 announcement, the company claimed this single chip is 48 times faster than NVIDIA GPUs and 8.5 times faster than Cerebras accelerators. They call this architecture a hardcore model. Instead of storing an AI model's weights in high-bandwidth memory and constantly fetching them to process data, the specific weights and data flow of a single model are cast directly into the physical transistors. AMD is making a very specific calculation here. They are betting that if you are willing to freeze a model state, the cheapest and fastest place to keep the weights is permanently baked into the silicon itself. This approach takes a problem we usually solve through software optimization, inference pricing, and converts it entirely into a manufacturing cadence challenge. Under this architecture, when a new model is released, you cannot just download a software update. Model churn becomes a physical mass cost. You have to manufacture new hardware. To evaluate this deal, we have to look closely at the Respin economics required to make a disposable chip viable and examine the unverified caveats hiding just beneath the press release. If we want to know whether this acquisition actually threatens NVIDIA's dominance, we have to look past that 5-figure throughput and analyze the brutal realities of silicon amortization. The HC1 achieves its speed by entirely eliminating the memory bandwidth bottleneck. There is no moving data between memory chips and compute cores. It is, in the most literal sense, a model-specific integrated circuit, a chip built to run exactly one model and nothing else. Because the model is frozen into the hardware, the economic viability of this architecture rests on reducing both the cost and time it takes to manufacture a brand new chip when a better model comes out. Updating a chip for a new model means changing just 2 layers out of 100. The bottom 98 form a model-agnostic base wafer, stockpiled in advance. The model itself is a metal patch, committed to those final 2 layers. By only altering those final layers, Taalas claims they can achieve a 2-month silicon turnaround from the moment a target model is locked in. This physical lock-in is the exact inverse of the other major architectural trend we are seeing right now: hardware-software co-design. In co-design, projects like DeepGrove's Maple Preview alter and compress the AI models themselves so they can fit onto cheap commodity hardware. They trade a bit of output quality in exchange for deployment flexibility. Instead, Taalas goes in the completely opposite direction. They bend the physical hardware around a rigidly frozen model. This trade-off allows you to keep exact model weights and achieve massive throughput, but you sacrifice all post-deployment flexibility. If that 2-month turnaround claim holds true in production, the model-specific integrated circuit evolves from a punchline about obsolescence into a viable strategy for amortization. Understanding the silicon is only half the equation. We must also look at how infrastructure builders will deploy these chips in a data center. Right now, the HC1 is purely a technology demonstrator. It serves a single 8 billion parameter Llama model behind a simple chatbot interface, and there is zero public pricing available for the chip, the tokens, or the acquisition itself. AMD integrates this technology inside EPYC-powered Helios racks using a disaggregated split. Standard AMD Instinct GPUs handle the compute-heavy prompt prefill. Once processed, the workload is handed off to hardwired Taalas chips, taking over solely to rapidly generate output tokens. Splitting the workload like this is highly efficient for decode-heavy applications, but it introduces a severe production cadence problem for the end user. By adopting this hardware, users inherit significant latency. You face a minimum 2-month floor from the moment you lock your model choice to the physical creation of the silicon. Add to that TSMC fab queue times and the logistics of physical rack deployment. You are looking at a multi-month hardware pipeline, operating in an industry where frontier open-weight models are currently iterating on a nearly monthly basis. There is a potential mitigation for this rigid lock-in. Back in February, Taalas Materials mentioned the chip supports LoRA fine-tuning and configurable context windows. To allow fine-tuning, those specific adaptation layers must live in writable SRAM memory on the chip, while the vast majority of the base weights remain permanently frozen in the metal. However, the company has not published the maximum adapter size limit, nor have they detailed the speed penalties that occur when the chip is forced to rely on that writable SRAM instead of the hardwired metal. Emitting tokens at 5 figures per second is exactly the shape serving stacks want right now, but that raw speed becomes a liability if it leaves you locked into a model you were forced to choose a full quarter ago. This brings us to the final and most critical caveat of the acquisition: the reliability of the underlying performance numbers driving the deal. Every single performance claim generated in this press cycle comes directly from Taalas, measuring its own hardware. The benchmark they chose relies on a highly favorable, smaller 8 billion parameter model, and their own comparison chart specifies a strictly controlled operating point, a 1,000 token input and 1,000 token output sequence. This graphic shows a glaring discrepancy in how these claims were reported. Coverage of the exact same announcement stated the chip was 48 times faster than NVIDIA GPUs in one publication and 73 times faster than NVIDIA's H200 in another. When reports of the exact same press event disagree by a factor of 1.5 on the headline multiplier, that number is doing marketing work. It is not doing measurement work. There is a complete absence of independent third-party verification. Furthermore, there are no published output quality numbers comparing the hardwired model's accuracy against its standard FP16 reference counterpart. AMD is making a massive structural bet here, and the economic justification for it rests entirely on that unverified 2-layer, 2-month Respin claim. That rapid manufacturing turnaround has never been demonstrated publicly across even a single model transition. The HC1 test chip is the only silicon the public has seen, and the deployment schedule for its successor, the 20 billion parameter HC2, is already showing distinct inconsistencies across different industry sources. Going forward, there is a clear architectural kill signal to watch for. If the first AMD-era Taalas silicon ships hardwired to a model that is already 2 generations stale, the 2-month turnaround claim will have failed its first contact with reality. The success signal is the exact opposite: an independent benchmark of a Taalas chip serving a model that was released to the public after the chip's base layers taped out at the foundry. With this deal, AMD is placing a high-stakes, unverified wager that physical manufacturing can finally keep pace with the velocity of AI research.